Okay, this is Clinton Weir. I'm documenting my final project for CSC 535, Deep Learning for Spring 2024 at the University of Illinois in Springfield. This is the first video. We're looking at my loading images script, my Python script. This and other code that I'm showing you is the code running on my local machine. I've had a number of issues trying to get this. I had a number of issues trying to get code running on Google Collaboratory, related to resource limitations and session timeouts and such. So by necessity, I've developed on my home machine, and I'm porting to Google Collaboratory. But for now, we'll just look at my code on the home computer. So this script has a lot of code that's going to look familiar. It's code that we've used throughout the semester. I've got where I put in the image size. I put in various common factors to my images dimensions. That way, if I need a reminder of the dimensions that are options for me. My batch size 64. The image size will be used here when reading the images from the directory. It'll be used later. It'll be used later in the training function calls. Some modification here. Okay, I don't think that shouldn't make a big difference, but there I modified that. I think it'll read the images from the directory in alphabetical order, so that needed an update. But yeah, so I've got code here to join to create the path. I think I could have just concatenated the strings using the plus operator, but alas, this is code that was recommended when I was looking for help with how to at some point this is the code that was recommended to me. But yeah, I think I could have just done a string concatenate. This function, we've used it in the class to read the images into each of these function calls. Will read from the directory given. It will look for subdirectories. It will read the images from the subdirectory, and each subdirectory is a class. So the subdirectories in this training directory, in this validation directory, in the test directory, the subdirectories have similar names, so that the each name is a class. Disk is. I don't think the directory names are not the same as what we see up here, and that's an oversight. But the names obviously relate to these categories. But yeah, so you have training, which is what we will train the data sets we'll use when we're those are the directories that will get passed into the model when we're training. The validation will be used during the training process to estimate the progress of the training, and will be used in early stopping. Validation is validation data set is an approximation of how the network will perform on data it has not encountered before. We'll eventually use the test data set to, formally as data that the network hasn't seen before. This is important because even though we're not showing the data, that we're not showing the network the validation data during training. We're not passing, it's not updating the network weights based on the validation data set. We are going to tune, so it could potentially be, if we train enough models, it's possible that just by chance we will find a model that performs well against the validation data set and does not perform well against data other data that the model has not seen. So that's what the test data set's for. So that explains these three. The batch size is 64. If you make that, so that's the this is the number of images that will be passed at once into the, when training. You use so this is related to how frequently the weights in the network will be updated. If you make it too small, it'll take a long time to train your network. The smaller batch size is associated with longer training times. A larger batch size is quicker, but you're not updating the weights as frequently, so it takes longer to converge, and also a large batch size uses more memory. So that's a trade-off. 64 is somewhat arbitrary. I could have made it larger because I have plenty of more than enough memory. I have 32 gigabytes on my computer, so I could have made so memory is not necessarily a limiting factor. I think I have more memory than what I would have available in Google Colab, although to be fair, if I was using Google Colab, I wouldn't also have to, I don't think I would be devoting as much memory to like an operating system and other programs running. So but I could make my batch larger. Memory wouldn't really be a problem, but then I wouldn't be updating my weights as many times. I could make it smaller, but that would take longer to to train. Of course, that neither of those statements those statements both true and both motivating factors in deciding a batch size. My statement does not inform why I picked 64 in particular. Like I said, I could have made it bigger. I didn't have a memory constraint. Could have made it smaller, and it would have taken longer. But I'm not saying that the training time was a problem necessarily. So yeah, 64 is pretty arbitrary. I'm afraid I don't have much more to say about that. One issue that I will bump up against later, I'll be introducing confusion matrix code. I use code basically that came from the class that we've used in the class to display a bland textual representation of the how the model performed for each class. Then later I'll use a prettier confusion matrix, but setting that aside, the confusion matrix code that I wrote doesn't work well with the train dataset or the validation dataset. It is clearly giving incorrect information because if you calculate the accuracy on those datasets and you compare it to the accuracy as reported when you use the evaluate function for that model, you call the evaluate function on the model object. Not sure if I'm using the right verbiage, right jargon for Python, but apologize. But yeah, if you use evaluate method on the model object and you pass the train or validation data set, you get in some cases you get a really good accuracy. Then when you use the confusion matrix, when you produce a confusion matrix on the same data set in the same models, you often get just junk results, meaning much lower accuracy, almost as if the predicted and actual labels are not in the same order. The actual labels and the images for the actual label list and the images for the predicted label list would give the appearance of being in conflicting, inconsistent order. So that is where my mind is led by the discrepancy between the accuracy as reported from these two methods of creating an estimation of the accuracy. And so the train data set has this issue, the validation data set has this issue, test data set does not. And so my mind, reviewing this code, my mind ponders whether it could be related to the test data set not being shuffled. Maybe in the code that I'm using for the confusion matrix may be, it's shuffling the images, whereas the actual label, the code that I'm using to get the actual labels, maybe it doesn't shuffle it. So then that would mean that the actual and predicted labels would be in different orders. They would, in terms of what images the labels are associated with. And if those two lists are in different orders, then obviously you're going to get even if your model is perfect, you're going to get really bad accuracy. Probably you would expect that the accuracy would be, let me say this a different way, that I'm not equipped to explain the thought that I'm having, but it would not, the accuracy that you expect if the two lists are sorted in different ways, it's not, you wouldn't expect it to be 1 over the number of categories, or 20%. It would be, I'm not sure if it would be, it wouldn't be 1 over 5, because the different categories have different numbers of examples. So, I think, I'm not equipped. But it would be related, it would relate to the number, the number of, well, let's just say the accuracy would approximate random chance. That if you had a perfect model applied to a sorted, a desorted list, predicted labels based on a perfect model applied to a desorted list compared to the actual labels in a sorted list, so an inconsistent ordering, you're gonna get accuracy that does not reflect, let's just say that you're going to get an accuracy figure that does not reflect the quality of the model. You're going to get something that reflects maybe, so like, I want to say the accuracy that I tend to get when the model is semi-random is like 40-ish%. I think that it would be the sum of the squares. This is me going out on a limb, but I think it would be like the sum of the squares of the percentage of the different classifications. So like if you had 80% of this label and 20% with that label, it'd be like 60, your accuracy, and you'd have 80% in the, you had the same, if you had 80% and 20% in the actual labels, and you had 80% and 20% in the probably predicted labels, and they're inconsistently sorted, I think that your accuracy would be 80% squared plus 20% squared, which is 64%, 20% plus 4, so like 64%. And maybe, A equals X for X in range 100. B equals, that's not right. A equals X for X in, I need to import random. Actually, from random import choice. Random, then choice. But, oh God, I want them to be weighted. I know this is gonna be dirty, but so I could do A equals 1 if X less than 20, else 2 for X less than 2, else 2 for. Okay, let's see. No? Oh. So I got a random distribution of numbers, either 1 or 2, and 80% is the, well, let's see. Let's make it 0 and 1. And then I can sum of A 76. God, I don't want it to be that. Oh, whatever. And then B equals 1 if index is less than 76, else is else 0 or blank index in range 100. Because sum of A is 76. So that means 76 of the numbers are 1. So print B, print sum of B, 76. So both are random distributions of 0 and 1, where both distributions, and so both distributions are both lists have 1 76% and 0 is 24%. So if my theory is right, then it should be 63.52% accuracy. Let's see. For AB in zip, AB, C, print C. I don't like that. C equals 1 if A equals B, else 0. C, print C, sum of C. No, I'm way off. I'm way off. Okay, so it's 0.76 times 0.76 plus 0.24 times 0.24. Yeah, that's right. I mean, I guess it's not that far off, but let's try again. We might need to make A. We might need to make A and B, you know, put a lot more values. Sum of well, no, let's try just making them a lot bigger. Wait, sum of A, sum of B, sum of B if B and A need to have the same number of members. Okay. So we said sum of A, sum of B, 0.7964 times 0.7964 plus 1 minus 7964 times 1 minus 0.79. There's probably a quicker way of doing that. Gosh, I guess that's possibly close enough. Maybe just make it that much bigger. Sum of A and sum of B. Good, print. Wait, how did I do the, okay. Oh, damn it. Print A, sum of, I don't need to say print, do I? Okay, so 0.79937, okay. X equals sum of A divided by 1 million. Y equals sum of B divided by 1 million. Sum of C. Okay, so then X times X, wait. X times X plus Y times Y times 1 million. Print the sum of C. Okay. Okay. So that shows that if two lists have the two lists, you take one list with two members, two distinct members, and then you randomly shuffle them. Then, and a list with two different distinct members, with one member is A, where one of the members appears in the list the number of times equal to A, and the other appears a number of times equal to B. And so you have a list, then you shuffle it, and then the number of times the members in the one will equal the members in the other for a specific position will be A times A squared, B squared, A squared plus B squared, as percentages. So it's anyway, I don't know if I'm explaining this very well, but this is, I think this is why when I try to make the confusion matrix using the training set or the validation set, I just get I get wonky results. I think it's because I am shuffling the images in these two sets as part of the prediction call and then when you compare it to the actual labels, you're not comparing the predicted label for this image. You're not actually comparing it to the actual label for that image. And then of course, then you're going to get, even with a perfect model, then you're going to get results that should be proportional to the sum of the squares of the probabilities of the classes. Again, assuming that you have a perfect model, with meaning the model would predict the correct label for every member of the set. And I don't think I'm going to be able to find in this code the distributions, but I think that's what's going on, why my confusion matrix code is not working, which isn't the subject of this video. This is why I don't like to this is why I didn't was reluctant to make this video, because I tend to have trouble staying on topic. But yeah, now I don't have to try to explain this. When we actually look at the confusion matrix, I can just say, hey, go back and look at the first video. And I'm just gonna end the video here. We're gonna move on to the next topic in the next video.